Hello, hi. I am Nurul Hazlina binti Nordin from UMPSA STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Welcome to Micro-credential 2, Raspberry Pi Installation and Configuration. This course is part of a structured learning series that integrates Python programming with hardware, enabling students to build real-world projects using the Raspberry Pi 4 and Raspberry Pi Pico microcontroller. This course is the second installment in the three-part series, which are Micro-credential number 1, Learning Python through Slider Game Development, where students develop programming fundamentals through an interactive game. Micro-credential number 2, Raspberry Pi Installation and Configuration, our current course focusing on setting up the configuration of Raspberry Pi on hardware interaction, and Micro-credential number 3, Raspberry Pi Programming, where students take their skills further by coding interfacing with external components. In this Micro-credential number 2, we will cover the essential steps to prepare Raspberry Pi for software and hardware integration. By the end of this course, students will be able to confidently install, configure, and operate a Raspberry Pi, laying the groundwork for more advanced application in embedded system and Internet of Things projects. This course is divided into 5 key chapters. Chapter number 1, Introduction to Raspberry Pi and its variants. This is when students will explore different Raspberry Pi models and their capabilities. Moving on to chapter number 2, students will learn into setting up Raspberry Pi. They will learn how to install an operating system and configure the device for first-time use. Chapter number 3, using a headless setup, where there is no monitor required. Here, students will learn on how to set up remote access to control Raspberry Pi from another device. Chapter number 4 is about Basic Command Line Interface, CLI, and terminal usage. Here, students will understand essential terminal commands to manage file, processes, and network. Last but not least, we will look into GPIO pin overview and basic electronics. This is when students learn to interface the Raspberry Pi with sensors, actuators, and other hardware components. One of the major projects in this course includes coding for the UMPSA STEM Cube, which is a Pico satellite simulation, where students will apply control structures to manage data collection and processing. This hands-on approach will allow students to bridge the gap between software and hardware, fostering problem-solving innovation.
Hello, hi. I am Nurul Hazlina binti Nordin from UMPSA STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Welcome to Chapter 1, Introduction to Raspberry Pi, our micro-credential course on Raspberry Pi installation and configuration. This course is designed to provide you with the fundamental knowledge required to set up and configure a Raspberry Pi. By the end of this course, you will be able to install and configure a Raspberry Pi for various applications. In Chapter number 1, Introduction to Raspberry Pi, students will explore diverse range of Raspberry Pi models, their differences, and their common applications in real-world projects. By the end of this lesson, you will be able to identify various Raspberry Pi models, including Raspberry Pi 4 and Raspberry Pi Zero. You will understand the key differences between different Raspberry Pi variants, such as power processing, connectivity, and expandability. Lastly but not least, you will recognize the common use cases for each model, from IoT applications, AI projects, to robotics and edge computing. The Raspberry Pi is a credit-sized computer designed for IoT automation, robotics, and learning. It runs on Raspberry Pi operating system, a lightweight Linux-based operating system. One of its key features is GPIO, also known as General Purpose Input-Output Pins, which allow it to interact with hardware components like LED, sensors, and motor. Python is the primary programming language used on the Raspberry Pi, making it an excellent tool for learning programming and developing real-world applications. The Raspberry Pi 4 is a compact yet powerful single-board computer. Let's break down its key component and understand how they work together. First is the processor, the CPU. At the heart of the Raspberry Pi 4 is the Broadcom BCM2711, a quad-core Cortex A72 processor running at 1.4 GHz. This processor handles all computational tasks, from running operating system to executing complex programs. It also includes an integrated Video Core 4 GPU, which supports dual 4K display and hardware-accelerated video decoding. Next, let's have a look into its RAM, the memory. Raspberry Pi 4 comes with multiple RAM options, 2GB, 4GB, or 8GB of LPDDR4 memory. More RAM allows for smoother multitasking and better performance in applications such as web browsing, programming, and even AI processing. This is where you insert your microSD card into the microSD slot. Unlike traditional computers with built-in storage, the Raspberry Pi 4 uses microSD card as its primary storage medium. The operating system, applications, and files are stored here. These are the USB port and connectivity. The Raspberry Pi 4 has two USB 3.0 ports and two USB 2.0 ports, allowing high-speed data transfer for external devices such as flash drives, external drives, and peripherals like keyboards and mice. It also introduced Gigabit Ethernet port, providing high-speed wired network connectivity. This is the wireless communication unit. Wi-Fi 802.11 AC is built into the board, allowing for wireless internet access. Bluetooth 5.0 enables connection with wireless peripherals such as speakers, game controllers, and data sensors. The Raspberry Pi 4 is also equipped with display interfaces. The Raspberry Pi 4 supports dual 4K monitors via its two micro HDMI ports, a significant improvement over its previous model. These ports allow you to connect monitors or TVs for an enhanced desktop experience. This is the power supply and power management unit. Now, note that this Raspberry Pi 4 requires a 5V 3A USB Type-C power supply to function efficiently. It includes improved power management, allowing for better stability under heavy workload. Now, this is where the 40 pins GPIO header is. One of the most important features is this GPIO. These 40 GPIO pins allow you to interface with external sensors such as LEDs, motors, and also other hardware, making this Raspberry Pi a powerful tool for physical computing and IoT applications. Now, these camera and display ports enables connection with Raspberry Pi camera module for projects involving computer vision and photography. The DSI display series interface ports allows the use of a Raspberry Pi touchscreen display, where this is the stereo audio jack. The Raspberry Pi Pico is a compact and energy-efficient microcontroller board designed for embedded systems, automation, and IoT applications. The Pico is built around a microcontroller and is optimized for low-power applications. Let's break down its key components. The main microcontroller is the processor RP2040, which is the Raspberry Pi microcontroller. It is a custom-built dual-core ARM Cortex M0 processor running at 133 MHz. Unlike Raspberry Pi 4, which runs on an operating system, the Pico executes programs directly from its flash memory, making it ideal for real-time processing tasks like sensor interfacing and motor control. Here is the memory. The Pico has 264 KB of SRAM, which is sufficient enough for most embedded applications. Instead of using a micro SD card for storage, it comes with a 2 MB of onboard flash memory, where users' programs are stored. The Pico operates at 1.8 volt to 5.5 volt, making it highly flexible for battery-powered applications. It can be powered via USB or external power sources, such as batteries or regulated power supplies. The Raspberry Pi Pico features 40 GPIO pins, many of which support path width modulation or PWM, ADC analog to digital conversion, and digital I/O. This includes a 3 12-bit ADC channels which allow it to interface with analog sensors, something standard Raspberry Pi model is lack. Unlike the Raspberry Pi 4, the Pico does not have built-in Wi-Fi, Bluetooth or Ethernet. However, it can be connected to external modules such as ESP8266 or ESP32 for wireless communication. The Raspberry Pi Pico includes a USB 1.1 port which serves two functions. Programming interface. This is where the Pico can be programmed via USB by dragging and drop UF2 files or USB devices or host mode. It acts as USB device like keyboard or mouse or even a basic host in some applications. A unique feature of Pico is its programmable I/O (PIO) blocks, which allows custom protocols and high-speed data transfer without using the main processor. This is especially useful for handling LED matrices, signal processing, or even VGA output. The debugging pin, such as the one shown on the left-hand side, make Raspberry Pi easier for developers to debug code using external hardware like a UART to USB adapter. It supports microprogramming in MicroPython and C or C++, making it accessible to both beginners and advanced users. The Raspberry Pi Pico is designed for low power application, consuming only a few milliwatts when idle. This makes it ideal for battery-powered projects like the one used in remote areas and remote sensors and wearables. The 3.3 fixed output buck boost SMPS converter for regulating the power supply. This is an onboard buck converter switching regulator that efficiently steps down voltage from the USB input, typically 5 volt, to the 3.3 volt required by the RP2040 microcontroller and other components. The boot select button on Raspberry Pi Pico is used to put the microcontroller into USB mass storage method. The boot cell button on the Raspberry Pi Pico is used to put the microcontroller into USB mass storage mode, allowing users to flash firmware into the device. So this boot cell becomes very important when you want to flash MicroPython or CircuitPython or a custom UF2 file onto the Pico. Sometimes you would like to recover from a firmware error or resetting the Pico to load a new program and switching between different firmware, example from MicroPython to C or C++ or CircuitPython. Take note that the Raspberry Pi Pico features a built-in 12 MHz crystal oscillators, which provides a stable clock source for the RP2040 microcontroller, ensuring precise timing for processing, communication, and peripheral control. The Raspberry Pi Pico is a powerful yet energy-efficient microcontroller, optimized for embedded applications, automations, and real-time processing. While Raspberry Pi Pico lacks an operating system, Wi-Fi and HDMI output, its versatile GPIO, ADC, and PIO capabilities make it an excellent choice when it comes to projects involve electronic system, robotics, and IoT. Both the Raspberry Pi 4 and Raspberry Pi Pico feature GPIO pins, allowing them to interface with external components such as LEDs, sensors, and motors. Now, these GPIO pins are being clustered into a couple of groups. The first one is the power and ground pin. Both boards provide power output pins to supply external circuit. 3.3 pins used for powering sensors and modules that operate on 3.3 volt logic. 5 volt pins, only on Raspberry Pi 4, used for higher power components like motors and display. The Pico lacks 5 volt GPIO, as it is strictly available only for 3.3 volt device. Ground pins are used for common ground connections for circuits and peripherals. Secondly is the standard GPIO pins. Both boards have general purpose input-output GPIO pins, which can be configured into input mode to read digital signals such as from buttons or sensors, and output mode to send digital signals, such as turning on LEDs or controlling relays. Raspberry Pi 4 has 26 GPIO pins, whereas Raspberry Pi Pico, even though it has 26 GPIO pins, it allows more flexible usage, including analog input, which is not available in Raspberry Pi 4. The third cluster is PWM pins, or stands for Pulse Width Modulation pins. PWM pins are used to generate variable signals, such as dimming LEDs or controlling motor speeds. Both boards support PWM, but the Pico has more flexibility, as any GPIO pins can be used for software-based PWM, while the Pi 4 has dedicated hardware PWM channels. The final cluster is the communication protocol pins. These pins are divided into 3 main groups, which are I2C, SPI, and UART. I2C stands for Inter-Integrated Circuit, which is used to communicate with sensors, displays, and other low-speed peripherals. Raspberry Pi 4 has 2 I2C buses, while Raspberry Pi Pico allows 2 I2C controllers. The second class is SPI, which stands for Serial Peripheral Interface, used for fast data transfer such as with SD cards and high-speed sensors. Both boards support 2 SPI buses, but Pico allows dynamic selection. And the final class is the UART, which stands for Universal Asynchronous Receiver Transmitter. These pins are used for serial communication between devices, like connecting the Pis to the GPS module or microcontrollers. Raspberry Pi 4 has one primary UART with an additional software configurable UART, while Raspberry Pi Pico has 2 UARTs with more flexible in-pin assignment. Raspberry Pi 4 has a more structured GPIOs layout with dedicated 5-volt pins, hardware PWM, and I2C or SPI or UART channels, whereas Raspberry Pi Pico more flexible pins assignments, support analog input ADC, and introduces programmable I/O (PIO) for custom communication protocols. Now, let's compare the different variants of Raspberry Pi. The Raspberry Pi family includes models such as Raspberry Pi 4, Raspberry Pi 3B+, Raspberry Pi Zero, and Raspberry Pi Pico. Each of these models has unique features suited for different applications. Let's break down the key differences. The first one is the processor. The processor is the brain of the Raspberry Pi. Newer models such as Raspberry Pi 4 have a more powerful quad-core Cortex-A72 or A76 processor, making them faster and capable of handling more complex tasks. The Raspberry Pi Zero, on the other hand, uses a simpler single-core ARM11 processor, making it suitable for lightweight applications. Secondly is RAM or Random Access Memory. Now, this RAM determines how well the Raspberry Pi can handle multitasking. The Raspberry Pi 4 offers up until 8 GB of RAM, making it ideal for running multiple programs or even desktop applications. The Raspberry Pi 3B Plus has 1 GB of RAM, while the Raspberry Pi Zero has only 512 MB, limiting its performance to basic tasks. The Raspberry Pi 4, which is designed as a microcontroller, has just 264 KB of RAM, as it is optimized for embedded system rather than full operating system. Next, let's look into the connectivity. Different Raspberry Pi models offer various connectivity options. The Raspberry Pi 4 and 3B Plus support Wi-Fi, Bluetooth, and Ethernet, allowing for easy network access. The Raspberry Pi Zero has no built Ethernet, though it does support Wi-Fi. The Raspberry Pi Pico, being a microcontroller, has no built-in network capabilities and is instead designed for hardware-level control. Next, let's have a look into USB ports. The number of USB ports determines how many peripherals you can connect. The Raspberry Pi 4 includes 4 USB ports, including 2 USB 3.0 ports for high-speed data transfer. The Raspberry Pi 3B has 4 USB 2.0 ports, while the Raspberry Pi Zero has only 1 micro USB port, requiring an adapter for regular USB devices. The Raspberry Pi Pico does not have USB ports for peripherals but includes a micro USB power and programming. Finally, let's have a look into its GPIO capabilities. This GPIO allows Raspberry Pi boards to interface with sensors, motors, and other hardware devices. The Raspberry Pi 4, 3B Plus, and Zero all have 40 GPIO pins, making them versatile for electronics projects. The Raspberry Pi Pico also has 26 GPIO pins, but is designed specifically for microcontroller-based projects, offering additional flexibility for embedded system. Now, let's have a look into each special features. Each model has unique strength. The Raspberry Pi 4 supports dual 4K display, making it a powerful mini computer. The Raspberry Pi 3B Plus is a great all-rounder for IoT and robotics projects. The Raspberry Pi Zero is ultra-compact and power-efficient, perfect for portable applications. The Raspberry Pi Pico is a microcontroller designed for embedded system and hardware control. The options of this Raspberry Pi depends on project requirement. Now, the most recent Raspberry Pi 5, for example, is the latest and most powerful model. It features 2.4 GHz Cortex-A76 processor, 8 GB of RAM, and PCI expansion support. Well, this Raspberry Pi 5 offers a significant performance boost compared to previous model, making it ideal for AI, edge computing, and high-performance applications. In comparison, the Raspberry Pi 4, the Raspberry Pi 3B, such as the one shown here, offers a balance between affordability and capability. The Raspberry Pi Zero is a compact low-power option for IoT, and the Raspberry Pi Pico is a microcontroller designed for embedded systems. With these options in mind, selecting the Raspberry Pi depends on your project needs, whether it's a full computing experience, IoT development, or real-time embedded system.
Hello, hi. I am Headless from UMPSA STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Welcome to Chapter 2, Setting up Raspberry Pi of our Micro-credential course on Raspberry Pi installation and configuration. This course is designed to provide you with the fundamental knowledge required to set up and configure Raspberry Pi. By the end of this course, you will be able to install and configure Raspberry Pi for various applications. By the end of this chapter, You will be able to prepare the SD card for installing an operating system on your Raspberry Pi, install Raspberry Pi operating system, ensuring you have the right setup for your project, configure essential system settings such as network connectivity, language preferences, and initial setup options, and update and manage software packages, keeping your Raspberry Pi secure and up to date. These foundational steps are crucial to getting your Raspberry Pi ready for development and experimentation. Let's begin. The official Raspberry Pi OS is Raspbian, based on Debian Linux. To install it, download the Raspberry Pi imager from the Raspberry Pi website, flash the OS onto a micro SD card, and insert it into the Raspberry Pi. Choose the suitable operating system type. Choose the SD card for the Raspberry Pi OS. Click on Write. Insert the micro SD card into the Raspberry Pi and turn the Raspberry Pi on. Follow the setup instructions. When booting Raspberry Pi for the first time, you need to set up the language, keyboard, and Wi-Fi. Update the system using sudo superuserdo apt update and sudo apt upgrade. Enable SSH and VNC for remote access.
I am Nurul Hazrina binti Nordin from UMTSA STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Welcome to Chapter 3, Headless Setup of our Micro-credential course on Raspberry Pi installation and configuration. A headless setup means running Raspberry Pi without a monitor, keyboard or mouse. Instead, you access and remotely using SSH or VNC. To do this, we will need real VNC. So, what is a real VNC viewer? Real VNC viewer provides a seamless way to remotely access and control your Raspberry Pi. So it allows you to remotely manage your Raspberry Pi from wherever without needing a physical monitor, keyboard or a mouse. It gives you an easy access whereby you can connect with multiple devices, including PC, Mac and even smartphones, making it highly flexible. And it supports secure connection. Real VNC ensures encrypted and secure remote access, keeping your data and system safe. With Real VNC, working with your Raspberry Pi becomes more convenient and efficient. Let's explore how to set it up. VNC or Virtual Network Computing operates by transmitting screen data from the Raspberry Pi, which acts as the server, to a remote device running the viewer. At the same time, it allows real-time input control, meaning to say, you can interact with your Raspberry Pi just as if you are using it directly. When you move the mouse, type on the keyboard or execute command, the actions are sent back to the Raspberry Pi over the network. Before setting up Real VNC, let's go over the essential requirements. First, the hardware requirements. You will need a Raspberry Pi running Raspberry Pi OS, a power supply, and a micro SD card with the OS installed. For the initial setup, a monitor, keyboard, and mouse are required to configure the system. Next is the software requirement. Real VNC server comes pre-installed with Raspbian, so no extra installation is needed. On the device you'll be connecting from, you will need to download and install Real VNC Viewer from the Real VNC website. Finally, network connectivity. For the initial connection, both Raspberry Pi and the viewing device, whether a Mac, PC or a smartphone, must be on the same network, same wireless access point. Once configured, you can enable cloud access to connect from anywhere. With this in place, you are ready to set up Real VNC and take control of your Raspberry Pi remotely. To connect your Raspberry Pi using Real VNC Viewer, you first need to find its IP address. Starting by opening the terminal on your Raspberry Pi. Next, type the following command, hostname-l. The command will display IP address of your Raspberry Pi. Make sure to note down this IP address. You will need it when connecting from Real VNC Viewer on your PC, Mac or smartphone. With the IP address, you are now set to establish a remote connection. To enable remote access, you need to configure your Raspberry Pi setting. First, open the Raspberry Pi configuration tool. You can do this by navigating the preference menu on the desktop or by entering the command sudo raspi config in the terminal. Next, go to the Interfaces tab. Here, you will find options to enable SSH and VNC. Turn both on to allow remote access. SSH enables secure command line access, while VNC allows full remote desktop control. Once enabled, click OK and restart your Raspberry Pi to apply the changes. Now, let's have a look on how to set up Real VNC Viewer. First, download Real VNC Viewer. You can do this by going to the Real VNC website, https://www.realvnc.com. Then, download and install Real VNC Viewer for your operating system, Windows, macOS, Linux, Android, or iOS. Once you have downloaded and installed, make a new connection. Now, when you click this new connection, you will be asked to include this IP address or hostname. Write that inside this bar. Once done, click OK. In the address bar, enter the IP address of your Raspberry Pi. To connect with the Raspberry Pi, enter connection details. Enter the IP address of the Raspberry Pi in the real VNC viewer and click connect. A security warning may appear. Click continue to proceed. Step number 2, authentication. Enter the Raspberry Pi username. Default is Pi. Unless you change, you can use this default name. And password default is Raspberry, unless change. So now, you can have your Raspberry Pi to be controlled remotely. Step number 2 is the authentication. Enter the Raspberry Pi username. Default is Raspberry Pi. Next is the authentication step. Enter the Raspberry Pi's username. Default is Pi. And password default is Raspberry, unless change. Click OK to connect. Sometimes you may face troubles, and to troubleshoot some of the common issues. Troubleshooting common issues in establishing this virtual network. Sometimes VNC server is not enabled. So recheck the setting in Raspberry config. Secondly, which is most common, is incorrect IP address. Ensure the IP address is correct and the Raspberry Pi is on the same network.
am Nurul Hazrina binti Nordin from UMPSA STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Welcome to chapter number 4. This chapter, Basic Command Line Interface, CLI and Terminal Usage. The command line is a powerful tool that allows you to interact with Raspberry Pi operating system efficiently. Whether you are managing files, installing software, or setting up permissions, mastering the command line is essential for working with Raspberry Pi. By the end of this lesson, you will gain essential skills to navigate and manage files in Linux environment for Raspberry Pi OS. First, you will learn how to navigate the Linux file systems using essential commands, allowing you to explore different directories and locate file efficiently. Next, you will be able to execute basic shell commands, including ls to list, for example, pwd to check the current directory, and cd to move between directories. These fundamentals commands are crucial for managing files and folders within the system. Next, you will also learn on how to install and manage software packages using the APT, the Package Management System in Raspberry Pi OS. This will enable you to install new applications, update softwares, and manage dependencies effortlessly. Lastly, you will gain an understanding of user permission and learn how to control access to files and directories. This is key security feature in Linux that ensures only authorized users can modify and execute specific files. With these skills, you will be equipped to operate the Raspberry Pi efficiently using the command line interface. Let's start. The command line interface or CLI plays an important role in programming. But why is it so important? Firstly is efficiency. The command line allows for faster execution tasks compared to the graphical user interface. Secondly is remote access. Many Raspberry Pi setups operate without a monitor, making remote control essential. With CLI, you can connect your device using SSH, allowing full control from elsewhere. Third, automation. It enables you to automate tasks using script, whether it's running system updates, managing files, or schedule operations. Finally, low resource usage. Unlike graphical interfaces, the CLI consumes minimal system resources, making it ideal for lightweight embedded systems like the Raspberry Pi. By the end of this chapter, you will gain hands-on experience with Linux command, helping you to see the full potential of Raspberry Pi. The shell is a crucial component of the Linux operating system. It serves as an interpreter, processing user inputs and executing commands. Unlike graphical interfaces, the shell provides a text-based user interface, allowing users to interact directly with the operating system. In the Raspberry Pi OS, also known as Raspbian, the default shell is Bash. Bash stands for Born Again Shell and is one of the most widely used command line interfaces in Linux. Using the shell gives users more precise control over the system, whether managing files, configuring networks, or automating tasks. Another advantage is remote control. Many Raspberry Pi setups are accessed remotely, and the shell allows users to control their devices via SSH without needing a monitor or keyboard attached. However, efficiency in using the shell requires some memorization. Mastering basic commands can significantly improve productivity and system management. Throughout this chapter, you will learn how to navigate Linux shell and use it to perform essential tasks on your Raspberry Pi. The terminal is a text-based interface that allows users to enter commands and view their output. Essentially, the terminal is the environment where the shell runs. When you open a terminal, you are launching a window that provides access to the command line interface. On Raspberry Pi OS, also known as Raspbian, the default terminal application is LX Terminal. This lightweight terminal emulator provides a simple and efficient way to interact with the system. Through the terminal, users can execute commands, manage files, install software, and control hardware, all without using a graphical interface. As we move forward, you will gain hands-on experience using terminal to navigate the Raspberry Pi system and perform essential tasks. The Linux system follows a structured hierarchical design. At the top of the hierarchy is the root directory, represented by a single /. From here, the system branches into multiple subdirectories, including important folders such as home, etc., and var, each serving a specific purpose. To navigate this file system efficiently, we use essential command line tools. The first command, pwd, for example, prints the current working directory, allowing users to see their exact location and their file structure. Next, we have ls, which lists files and directories within the current location, helping users explore their system. Finally, the cd command, which allows users to change directory, moving between folders at ease. Mastering these command lines is crucial for managing files. In Linux, text editor function much like word processors, but they are simpler and optimized for working within the command line. Some of the most commonly used text editors includes Emacs, Vi, and Vim, each offering unique features for editing and managing files. Apart from text editor, Linux provides quick way to view the file content. Commands like cat, head, and tail allow you to display files directly with the terminal. Cat prints the entire content. Head shows the first few lines, and tail displays the first few lines of the file. Next, let's have a look into how to manage packages with APT. Note that this is not apartment. APT stands for Advanced Package Tool. Now, APT is the package management system to install, update, and remove software. To update package list, use superuser-do sudo apt update. To install new package such as Python, type sudo apt install python 3. And to upgrade, type in sudo apt upgrade. In Linux, a process is simply the execution of a program. Each program you run, whether it's a text editor, script, or a system service, create a process. Linux is a multitasking operating system, meaning multiple processes can run simultaneously. To view activity processes, you can use the ps command. This will list all the running process along with their process ID. If the process becomes unresponsive or need to be stopped, the kill command can be used to terminate it. By specifying the process ID, you can safely end any running task. One important rule when shutting down a Linux machine is to never just unplug. Instead, always use shutdown command to power it off properly. This ensures all processes terminate safely and prevents data corruption. Understanding how to manage a process is crucial for maintaining system stability and efficiency. In this slide, we'll explore file permission and how to interpret the output ls-l command. First, the ls-s lists files in a detailed format, displaying their permission, ownership, size, and modification time, such as the one shown here. Now, let's break this down each column. The first column represents the permission, indicating who can read, write, or execute the file. The second column shows the number of hard link. A hard link is an additional reference to the same file on the file system. Unlike a shortcut, it directly links to the file's data. The file is only fully deleted when all the hard links are removed. The third and fourth column displays users or owner name and group name, both of which define who has access to the file. The fifth column indicates the file size in bytes, and the sixth and seventh column show the dates and the time of the last modification. The sixth and seventh column shows the date and time of the last modification. Finally, the last column is the file name itself. Understanding this structure helps us manage file access and security in Linux effectively. In Linux, file permissions determine who can access the file and what actions they can perform. The first character represents the file type. D means directory. Dash indicates a regular file. L represents a symbolic link. The next 9 characters define permissions for 3 categories of users. The owner, which is the user, the person who created or owns the file, group, other users who belong to the same group as the user, and others, everyone else on the system. Each set of these character represents permissions. R means readable, W means writable, X means executable, and dash means no permissions is granted. This is an example of a file permissions in Linux. The first character dash indicates that this is a regular file. The next 9 characters define the permissions for 3 categories of user. The owner, Hazlina, has read and write permissions, meaning she can view and modify the file. The group, Hazlina, has read-only permissions, meaning they can view the file but cannot modify it, whereas the others also have read-only permissions, allowing them to view but not edit the file. These permissions ensure that only the file owner can make changes. These permissions ensure that only the file owner, Hazlina, can make changes, while others can only read the content. So here, what it means is that for the file notes.txt, the owner, Hazlina, can read or write, while the groups and others can only read the file.
Hello, hi. I am Hazlina Nordin from UMPSC STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Welcome to Chapter 5 GPIO Pins Overview in our Micro-credential course, Raspberry Pi Installation and Configuration. In this session, we will explore how to use Raspberry Pi General Purpose Input-Output or GPIO pins to control external devices such as LEDs, buttons, and sensors. By the end of this lesson, you will be able to write Python programs to interact with Raspberry Pi and the GPIO pins effectively. By the end of this chapter, you will understand the layout of Raspberry Pi GPIO pin-out diagram. You can gain hands-on experience connecting external components to GPIO pins, and you can write Python scripts to control GPIO pins for input and output operations. GPIO, General Purpose Input-Output pins, allows Raspberry Pi to communicate with external components used to control LEDs, buttons, motors, sensors, and more. This pin can be programmed for input, reading data, and output, sending signals. This is an example of Raspberry Pi GPIO pin-out diagram. This is the Raspberry Pi 4 GPIO pin-out diagram. The Raspberry Pi has 40 pins. Category 1 is the power pin, 3.3 volt and 5 volt. Now these power pins are color-coded in red. The power pin provide power to the external component. The ground pins serve as reference points for the electrical circuits. Secondly is the ground pins, where they serve as the reference point for the electrical circuits. The third class is the GPIO pins, numbered 2 to 27, are the programmable and can function as inputs and output. And the final class are communication pins, which includes I2C, SPI, and UART for connecting external peripherals. We use rpi.gpio library in Python. This library provides a simple way to interact with the Raspberry Pi GPIO pins, allowing us to control electronic components such as LEDs, buttons, and sensors. The first step is importing the libraries. Before we can control the pins, we need to set the pin numbering mode. The Raspberry Pi has two ways of referencing GPIO pins. The first one is the BCM mode. This refers to the Broadcom GPIO numbering, which follows the internal hardware design of the Raspberry Pi. For example, GPIO 18 corresponds to a specific pin, but its location may vary depending on the Raspberry Pi model. The second mode is the baud mode. Now, baud mode uses the physical pin numbers on the Raspberry Pi's GPIO header. For example, pin number 1 is always in the top left corner of the baud. To select a numbering mode, we use the following command: gpio.setMode, GPIO BCM for Broadcom. Here is an example of Python codes for Raspberry Pi. Let's have a look. What is the typical structure of coding Python for Raspberry Pi? We begin by importing two essential libraries. In this case, it's rpi.gpio, which allows us to control the Raspberry Pi's GPIO pin. And secondly is time, which enables us to introduce delays in our code. Secondly is setting up the GPIO mode. So in this case, we configure the GPIO pin numbering mode. The Raspberry Pi has two numbering systems as mentioned earlier, BCM or baud. So in this case, we are using GPIO.BCM. And step number 3 is to configure GPIO 18 as the output, such as the one shown here. We set the GPIO pin 18 as an output pin, meaning it will send signals to the connected components such as an LED. And step number 4 is to write a blinking loop. We then enter continuous loop. So what is being mentioned here is that we will turn the LED GPIO 18 to high. We will wait for 1 second using the time.sleep function, and turn off the LED by setting the GPIO 18 to low. We wait for another 1 second before repeating the instructions.